This is the front page of the paper in question, and as you already, I believe, noticed, it looks very scary. And if you notice the first author, Oleg Kiselyov, you must be very scared at this point. So the story is so I learned about this paper quite a lot of years ago, and my friends were talking about it, and I couldn't make a clue what's going on here, because it's not something which a young Haskell developer usually knows from the very beginning. Like, you start with some lists and then it says monotransformers, terminating. No way. So I got some friends, they had a chat, and they basically told me this is just a paper about a better list monad. And it kind of makes sense for Haskell developer. And well, some years have passed, and I like to think that I'm kind of seasoned Haskell developer these times, and I can get back to this paper, and I can understand this paper better, like maybe I will be able to understand its original title. But it appeared that no, actually I understood that the real title is even simpler. It's just better list comprehensions. No talk about monads at all. So what are list comprehensions? Yeah, it's just a very well established mathematical notation. In mathematics we call it set builder notation, which basically says that we describe some sets of numbers or sets of tuples of numbers or whatever, like factor first, and after a bar we write down what are possible values for our variables. Like here we say that x is an integer number, let it be an integer for simplicity, an integer number between 1 and 3, so potentially it could be 1, 2, 3. And we say that y is between x and 4, and let's assume that it's also an integer number. So depending on x, we have different potential values of y, and we write down a couple of conditions on x and y, which will filter out our input. So for example, this set builder notation describes a set of 6 elements, of 6 pairs of integer numbers. And it's kinda nice. It's very terse syntax. We'd like to use it in our programming languages. And not surprisingly, in Haskell we have just like very similar notation. The only difference is that mathematicians usually describe intervals putting a comma between begin and end, and in Haskell we just put 2 dots. So just don't get confused. If I'm writing some Haskell codes and I denote intervals in this way, this is 1, 2, 3, and if I'm writing some mathematic formula, then I will write down, then I will denote intervals in that way. And this notion of list comprehension is quite useful and well established, and while Haskell boasts itself that it's very terse and very cool, we have it in Python. Like, the syntax is basically the same except some different syntactic sugar. We again say that we collect pairs for x in range, for y in range, if some conditions on x and y. Does anybody can give me an example of another language with list comprehensions? Maybe your favorite language, or...
Clojure.
Yeah, Clojure. Any more examples?
C++ 26.
Oh, a man of a culture. Any more examples? Maybe some exotic one? Okay. So PostgreSQL has this nice helper generate series, but you can emulate it in other SQL dialects with some other means, and basically it says exactly the same. It just generates a table between 1 and 3, it generates a table between x and 4, it forms a Cartesian product of these tables, filters them by a condition, and returns pairs. So it's very well established notion, very widespread, everything good. And we like to think that we can describe in Haskell, like almost any set builder expression which we can find in mathematics. But there are some caveats. So first one is that in mathematics we very often work with infinite objects. And it's kind of good. We all know, well, okay, most of us know that Haskell is very good when you need an infinite list of something. So we do not expect any trouble here. Like mathematicians can write this kind of expression. So this fancy n is a set of natural numbers, like 0, 1, 2, 3, 4, 5. And by multiplying it by 2, I just mean that I am speaking about even numbers, like 0, 2, 4, 6, 8. And so on ad infinity. And here is my filter. I say that I'm interested only in numbers, only in even numbers, which are divisible by 3, which basically give a remainder 0 when divided by 3. And this is like 0, 6, 12, 18, 24, and so on. Very well. And hooray, hooray, we can describe exactly this expression in Haskell without any unnecessary noise. Yeah? And it will work, kind of, because Haskell is a lazy language, and it will produce this list in a lazy manner, and it will filter it, and it will return us some results. Is all notation clear? Good. So this is a list generator. It generates an infinite list, starting with 0 and with a step equal to 2. Okay, and here is our next problem. We describe a set which is a union, yeah, easy to remember like a U, which is a union of a set of numbers which are divisible by 2 and a set of numbers divisible by 3, and our filter condition is that we are looking for basically odd numbers. And well, so fine, like every mathematician can quickly understand that no even number can be odd, so we can start with this set. So we're looking for numbers divisible by 3 and which are odd at the same time, so it's 3, 9, 15, and so on. Well, we can write the same expression in Haskell like this. What's going to happen? So basically nothing. Yeah, I'll just stuck forever with this first list. My compiler would make a lot of work. It would filter it hard with all my cores, and you know, I can use all my cores because Haskell is easily parallelizable on many capacities, maybe even on GPU if I'd like to. But no, it just returns, it just gets stuck. Why? The fundamental reason that it gets stuck is that this plus plus operator, which concatenates lists in Haskell, it's left biased. It prefers to first, it puts all elements of its left argument first. So when I write this, it would always put all this list at the beginning. And it's not what I would like to do. I'd like to somehow maybe fairly interleave both of my lists of input values, both of my input streams. So what I would like to have, I would like, instead of plus plus, I'd like to use some function interleave. It would take two lists of values, possibly infinite, possibly both of them are infinite, and it will like fairly interleave them until both of them are non-empty. And if they are of different lengths, it will just put the tail of the longer list as a tail of the result. And we can, so as I described it, if any of arguments is empty, then just return the second argument, and if both are non-empty, then take heads and return them and go on the recursive step. This is a simple implementation, nothing fancy at all. Is everything clear at this point? Okay. Can anyone tell me why we would like to look for a simpler implementation? Like this implementation takes 3 lines, we would like to have an implementation which takes 2 lines and works better, in some sense better.
I don't know Haskell at all, but it seems like you could have several in the left-hand side, like 1, 2, 3, and then the right-hand side 4, 5, 6. And so you want to put the 1, 2, 3 before the 4, 5, 6. But maybe this implementation would just do 1, 4, 2, 5.
Not really. I don't care about order of values at this point. Like, if you look at this type signature, it says that it works for any type A. And it means that I cannot expect that this type A is ordered. Not really, it's manual recursion anyway.
Maybe you have the match on the first one only, and then you use interleave of y and x.
Exactly. So the simpler implementation, which is shorter and is better, is this one. We check first argument. If it's empty, return the second one. If it's non-empty, then return its head and flip our arguments. So basically this one is one. Why this implementation is better? Because it's more lazy. If a list of ys is some values which take a lot of time to compute, but x's are something which you can compute fast, or maybe it's already given. This implementation, before it returns anything, like in this case, it will force evaluation of first argument and evaluation of the second argument. Yes, yes, but it's still some work.
Yeah, but what if to find the next cons basically takes you forever? So that's the, yeah.
So this one is much better, just computes to the weak normal form, technically speaking, the first argument, and immediately returns you at least one value, and then it proceeds to recursion. Okay, so the first struggle with a union is fixed. We can replace plus plus with this fair interleave operator. Why would we ever use plus plus actually? Can we possibly replace it with this fair interleave function throughout all our standard libraries, through all our Haskell libraries? Yes, but is it was it a prerequisite?
Especially if you want to combine signs.
Yes. One problem with interleave is that interleave is not associative. But plus plus is. This is just a side note. And here is another issue when we encounter infinite lists. So this is a simple set. Like we say that x is any natural number, y is any natural number, and return me those pairs of x and y such that x is greater than y. Cool. Very simple set. And let me, well, it's very simple, and I can just translate it into Haskell. Like I say, x is any natural number from 0 and forever, and same for y. And here is my condition. What happens? Is this computation productive? Would it ever return me at least first pair of values which satisfy our condition? Yes. You can, because what happens internally? Internally, we are just running 2 for loops, and once we enter the first one with x equal to 0, we are stuck forever in the second one, because we will check that if 0 is greater than 0, no, false, next y. 0 greater than 1, no, false, next y. So we are just stuck forever. Kind of, this problem looks similar to the previous one with interleave. Like we again encountered some infinite lists and we cannot move further, we are stuck. So what order? So in this problem we kind of walk through two-dimensional matrix of x's and y's. So we basically walk it in this direction. It's kind of biased, yeah? It's always, it prefers to go on horizontal lines, incrementing y's ad infinity, and only then, if y's is a finite list, it will return back, and so forward. So the implementation looks like this, of this unfair, of this biased interweaving of two lists. So it says what it says. If the first list is empty, then the product of these lists is empty as well. And if first list could have some element x in head and some tail xs, then map ys, making for each y in ys, return a tuple with x as a first component and y as a second component, and plus plus, go to the recursive call with smaller first argument. Any ideas how can we fix it and make it more fair? With what? Yes, interleave was a fair version of plus plus. Okay.
Use its leaf here that way.
We can go in. There are actually several possible solutions. There are several possible solutions. I'm showing you like a simple case of more general one. So the best way what we can do is literally, yes, we replace this, as someone told, replace plus plus with interleave. And we get this implementation, and this is the path of walk through our matrix of tuples. I mean, it doesn't look too too simple. I believe it's quite complicated schema, but basically the idea is that you always, like, each second time you go to this level, each fourth time you go to the next level, and for each 8 elements of this line you take one element of the third line, and so on. And this implementation allows us to basically be productive. We can return back here, yeah, and we can, instead of relying on some sugar inside of Haskell compiler, which will interweave these two lists, we can use our handwritten fair version of interweave. Sorry. Okay, more issues with our list comprehension. This is a definition of composite numbers. Number is called composite if it has at least one non-trivial divisor. Non-trivial means that it's not one and not itself. Like 5 is not composite number because 5 has only two divisors, 1 and 5. 4 is a composite number. Yeah, it's a composite number. It has a divisor 2. Like 6 is also a composite number. It has even more divisors. It has divisor 2 and 3 and so on. And we can write this condition in set builder notation. So let's find all composite numbers between 2 and 10. So we say, okay, x runs between 2 and 10, and this is my condition. I want to check that there exists such y, at least one, which is running over this list, such that x is divisible by y. X gives reminder 0 by modulo y. And yes, so the list of first composite numbers is this. And I would like to express this somehow in Haskell. So the most interesting part is, of course, what expression could be given to this quantifier of existence. I can try this, but obviously it's not quite satisfactory, because I asked just for a simple list of composite numbers, and what I get, it's much more information that I would like to have, and some numbers occur multiple times because they have more than one divisor. And probably I don't care about all divisors. I can possibly write it like this. So here I returned x and y. Here I'm returning just x, but not much better actually. There are still repetitions in this list. Yeah, and back to our SQL, this set builder notation is perfectly expressible in SQL. No troubles at all. We just generate two tables, we just have a condition, and then we just have this magical group by instruction, which basically takes this result and groups everything by unique access. So what can we do in Haskell? Really, is SQL so much better than Haskell? I should switch immediately. We can use nested list comprehensions. So basically what I say here is give me a list of x's such that x comes from this list, and the condition is that the list of y's in this from this list such that x mod y equals to 0, that all this list of y's is non-empty. So I have this internal list comprehension, inner one and outer one. And it's fine. We can actually introduce a handy helper once. So helper once would take any list and return list of the same type. So if it happens that its argument was an empty one, it will return empty list. And if it happens that this list, this argument is non-empty, it will return a list consisting of the head of the argument. So basically this is something very similar to that group by instruction in SQL. And yes, now I can express my computation in this form. I will return one of divisors of my composite numbers just as a witness that, yes, I checked. You can check after me. I am sure that it's composite. Here is an evidence. One evidence is enough? Yeah. So we use this once basically as aggregating operation in SQL.
Does Haskell have a set data type where at the top in math, it's a set builder notation, right? But
Yeah.
you're storing as a list. So if you
Good
just
question.
The second example to a set.
Good question. Yes, we have sets in Haskell, but they are not inductive types, technically speaking. So they have basically all sets, they require constraints that the elements are ordered, and they do not allow this kind, and they are strict in Haskell. So I'll get back to data types question later. It's true that working with lists when we intend to work with sets is kind of suboptimal and mildly infuriating. And one more quantifier for all. And an integer is called prime if it's divisible only by 1 and itself. So, like every integer is either 1 or composite or prime. So here is a set builder notation for prime numbers between 2 and 10. It's 2, 3, 5, 7. And what we say here is our source of access. And here is our condition that for all, not that there exist one, no, for all y's from this list, x is not divisible by y. So this is previously we worked with quantifier of existence, and here is quantifier for all. And we again can use nested list comprehensions to express it in Haskell in very much similar way. Like this time I'll say that here is in inner list comprehension, here is a list of y's which are divisors of x, and my filtering condition is that this list is actually empty. So this means that if there are no y's divising x, then for all y's, x is not divisible by y. And it's yet again expressible in SQL. We need help of left join operator. And in SQL we actually do it somewhat nicer, more declarative way. We just say that, make me left join of two tables and return me only those rows where y is null. So no y satisfies this condition. Can we express for all quantifier as quantifier of existence? Yes, as we did on the previous slide, we can say that this condition that for all y something is not equal to 0 is the same as say that it's false. This is a logical negation operator. It's false that there exists y such that something equals to 0. And we can introduce in our language for list comprehensions, we can introduce this combinator L not, which takes a list of anything, it doesn't care, and it returns a list of special type in Haskell. It's basically a type of nullary tuples. Like tuple can consist of 2 elements, like some very simple tuples can consist of 1 element, and this is like a tuple which has nothing aside at all. And obviously there is only one inhabitant of this type. This is just an empty tuple. So what I say, if my input list is empty, then I return a list with one element unit, empty tuple. And if my argument is non-empty, return empty list. The effect of this is that if I use the output of L naught, if I use its output in list here, say take X from this list and take some variable, I don't care about it, I'm not going to use it, so I'm not going to even name it. Take this unnamed variable from this list. So if this one inner list comprehension was non-empty, if there were any y's which divided X, then this list is non-empty, and the output of L naught is an empty list, and it says generate me X and an unnamed variable, and take a named variable from empty list. There are no way to take anything from an empty list, so all this computation becomes empty for each particular X, such that this list is non-empty. And if this list was empty, then L naught returns a list of one unit, and this part of my computation, it basically says, okay, take this unit from a list of one single element, assign it to this unnamed variable, and go on. And in this case, we pass through, and this X will be returned. This is kind of tricky part because this L naught is doing strange thing. It's just returning some. It returns either empty list or list of nothing, basically. Paper defines more general combinators. I'm kind of rounding some edges here. What next? So we discussed list comprehensions, and we discussed how can we introduce more operators to make list comprehensions in Haskell and basically other languages as well. How can we make them more useful to cover more use cases? We defined this very simple domain-specific language for list comprehensions of 4 operators: interleave, interweave, once, and L naught. So technical term is that this is a DSL for backtracking and relational logic programming on lists, because everything we talked about previously, it was only lists. Kinda nice. But yes, we'd like to work with some other data types, because lists not everything. We'd like to work with infinite streams of data which are actually infinite, and we'd like to work with values with associated probability. Like we can possibly model this multiverse model of quantum mechanics, where everything exists in all possible superpositions at the same moment. And we would like not only describe that there is a universe in which cat is alive and there is a universe in which cat is dead, we would like to assign some probabilities, that the probability of this universe where cat is alive is this one and cat is dead with this probability. And we would like somehow to manipulate streams of data. Like this is I have some list of cats which are dead or alive, and I have some list of dogs which are either dead or alive or chasing the cat, and I would like to make some relations between these objects and combine them and have some fancy predicates, and I would like to track somehow these probabilities from the input to the output. Another problem is that I'd like to handle side effects somehow. because it's all very nice when you describe this set builder notation. There are some infinite lists, and you like press enter, and it stacks. The big issue with this set builder notation list comprehensions is basically that you have no means of introspection. What's going on? I just hit button and it doesn't answer. Or maybe it answers something, but not what I quite expected it to be, and then it freezes for 10 minutes, and then it freezes for a day. I'd like to have some side effects to track this. I'd like to read input lists from possibly some I/O, like from disk, network, whatever. I'd like to cache some intermediate computations in some state monad, like. I'd like to track progress and write results, some intermediate results probably. So this is things which basically says that I want to have not just list of values, I want to have some state monad, reader monad, writer monad, I/O monad atop of my list. So this is a framework which was kinda requires more love. And we are finally back to paper. So what was the actual contribution of Kiselyov and company almost 15 years ago? What was their contribution to these problems which I described on this slide? They introduced, I'm sorry that I'm getting technical at this point, this is kind of very Haskell heavy definitions, but no other way. So Kiselyov and company, they introduced a type class monad logic, which basically captures these four primitives, these four combinators for our list comprehensions. And this type class is defined for arbitrary monad plus, which is monad plus something, which is behind the scenes at this point. So lists are a monad, but there are many other things which are also monads. And you can describe what these operators should do on anything which is monad plus. And authors also proposed nice